Hello, everyone. My name is Hyatt-Denesik, and we'll be talking about node connectivity augmentation via iterative randomized rounding. This work was done in conjunction with my supervisor, Laura Sanita, as well as Harris Angelidakis. So, as we've seen today, connectivity augmentation is the problem where you're given a graph G, connectivity value K, and some links and associated link costs. And you want to find the minimum cost subset of links, increasing the connectivity from K to K plus 1. And yeah, there's a standard approximation preserving reduction, bringing this down to only being worried about the cases where K is equal to 1 or 2. So when K is 1, we have the tree augmentation problem discussed by Vera earlier today. So in this case, the tree is just the black nodes and edges, and the links are the red edges. And if K is even, it becomes the Cactus augmentation problem, just discussed by Afruz, where, yeah, here we have in black the graph and in red the links. Yeah, so for the tree augmentation problem, it's got a very exciting history, especially recently, as you saw this morning. All sorts of interesting results. For the Cactus augmentation problem, work is quite a bit more recent, but still quite interesting. And kind of what we're interested in right now is the work that was just presented by Afruz just now, where what they did was reduce the problem to edge-based Steiner trees and then applying a certain Steiner tree analysis to it, and tailoring the analysis to those instances of Steiner trees. But this reduction, the way it was done, wasn't quite approximation preserving, because the links were the actual Steiner nodes and they had the cost, but they instead just treated it as a regular edge Steiner tree. So we're interested in these node-based Steiner trees. And that's sort of what we're going to use to solve the following problem, which is node connectivity augmentation, where node connectivity augmentation is the problem which has very little results, except recently it's been receiving some attention. Even the simplest version, which we'll be considering, which is one node connectivity, doesn't have much. In this case, you're given a graph with node connectivity value of 1 and some links, and you're trying to increase the node connectivity from 1 to 2. So there was a connection just last year found between node connectivity and Cactus augmentation. Basically, they both can apply similar reduction to go to the similar node-based Steiner tree instances. And that's what we're going to be doing to improve the approximation value for these node connectivity augmentation problems. In addition, Newton also found 1.6 approximation, 6 repeating, for so-called leaf-to-leaf instances, which is where links, both endpoints of a link are leaves. And so that will kind of come up in a bit, just a little bit. And so our results, we find a 1.892 approximation for one node connectivity augmentation. And thus kind of since they both use the same reduction, we find that similar approximation for Cactus augmentation. So some highlights of this talk. First, going to use this, going to go over this reduction from node connectivity to Steiner trees. We're going to look at the actual algorithm to solve these particular Steiner trees. And then we're going to give a little bit of a nice, simpler analysis for these rounding techniques, which again is tailored to these specific Steiner tree instances. As well, we're going to give specific cases which we call leaf adjacent, which is where links have one endpoint guaranteed to be a leaf, and the other one can be anywhere. And for this, we give an approximation ratio of 1.83 or H3. And we also give a lower bound on this analysis technique for these cases. So the actual reduction to Steiner tree is as follows. It's very similar to what we just saw from Fruz. In this case, up here is the augmentation problem that we start with, and below is the corresponding Node-Steiner tree instance. So for us, every leaf in the augmentation problem becomes a terminal in the Steiner tree problem. Every link becomes a Steiner node. Any link with a terminal endpoint is adjacent to that, or any link with a leaf endpoint is adjacent to that terminal in the Steiner tree instance. And yeah, for any two links that share an edge in their sort of projected path into the graph, they also have an edge between them in the Steiner tree instance. For example, these three links marked out with dashed lines, they all share this dashed black line here in G. So these three black nodes all are adjacent to each other. So we call these particular Steiner trees CA Node-Steiner trees, so connectivity augmentation Node-Steiner trees. And these possess the important property to us that every Steiner node is incident to at most two terminals. And with this, we can prove this theorem, which says that any alpha approximation for CA Steiner node instances gives us an alpha approximation for one node connectivity augmentation and for Cactus augmentation. And so we go about this using what's called the directed components relaxation, which is a certain hypergraphic LP originally designed for edge-based Steiner trees, but we're going to sort of define it for node-based Steiner trees. So you select from among the terminals just some root, and you create a variable for every component in this tree, where a component, roughly speaking, is some subset of k terminals and a choice of a sink. And we can view it basically as the minimum cost Node-Steiner tree connecting these terminals. And that's the cost of this component. So there's just a constraint to enforce connectivity here, where for every subset of terminals, not including the root, you just need a component which crosses this subset. And this is where we need this property that every Steiner node is adjacent to at most two terminals, because it should be pretty easy to imagine a problem where suppose you have one Steiner node, and that Steiner node is adjacent to 1,000 terminals. If k is 10, then you need 100 components in order to connect all of this. But the optimal solution is actually just like take the one Steiner node and connect it to everything. So you have a gap of 100 or as large as you'd like. And so that's sort of the problem. So because we have at most two terminals, we can prove this theorem, which just says that for any epsilon, you can find a k such that the optimal value of this LP is at most 1 plus epsilon times the optimal value of the integral solution, and that we can find it in polynomial time. And then so we can use this theorem for the following algorithm, which is the iterative randomized terming algorithm. So basically, in any iteration I, you repeatedly solve this instance that we have for this iteration, you get some solution xi. So suppose we solve the initial solution, and these are the three components we get, and they all have LP value 1/2. So you randomly select one of these components proportional to its LP value over the sum of all of the variables. So we randomly do this, and we find this green component here. So we contract it into its sink node, and then this is what we're left with, and we take that as part of our solution. When a single node remains, we're done. So we solve the LP again. We get this blue component here. We contract it, and we're down to a single terminal. So we return the two components, and this is what we find. And our cost is then just the sum of the two component costs. So then we want to know how much these components cost, and particularly how do we kind of relate the optimal solution at each of these contracted versions of G, and how do we relate that to the optimal value of G? And one way to go about this is if we imagine some fixed optimal solution T star, then we can imagine the procedure as basically taking this optimal solution T star, adding the component to it, and then going, oh, interesting, some parts of T star are made redundant by this, so we can just pull out these nodes. And then the question becomes, well, how many iterations in expectation until some node in T star gets deleted? And we can use this to bound the cost, and this becomes the actual the approximation ratio that we're looking for. And to solve this, we're interested in a kind of node-weighted spanning tree problem, where it's only node-weighted sort of indirectly, as you'll see in just a moment. So this node-weighted spanning tree problem is basically as follows. So here we have T star drawn in black and a terminal spanning tree with these orange edges here. And we want to pick this terminal spanning tree so that we minimize the following ratio, which is just the sum of the harmonic value of this function W of V divided by the number of Steiner nodes, which is the cost of T star itself. So W of V is the number of edges in W whose path in T star contains V. So for example, this node up top here has a 1 next to it. That's its so-called W value, because there's this one edge that goes, that projected into T uses it. This node here has 4 because there's 1, 2, 3, 4 edges that do this. And so we're interested in minimizing this ratio. If anyone's curious, this ratio applied to this graph has a 1.3 or 1.74. So we're going to give a way to construct such a terminal spanning tree so that this fraction has at most 1.8917. We also give an example, the leaf adjacent instance that I mentioned, which gives a 1.83. And also that there is a lower bound to this, so that for any choice of witness tree, not even the one that we use, it would go to 1.83. So to actually find this tree, what we do is we root the tree at some leaf, so this leaf 1, and we want to contract certain edges of this tree. And these edges are according to a minimum cost downward path from a Steiner node to a leaf, where the cost of a node is the inverse of its degree. So here we have these red paths corresponding to these minimum weight paths. We contract them, we end up with this tree here, which we just use as the witness tree itself, drawn here in orange, as you can see. So we use these particular weights because since we're trying to minimize a fraction that uses the harmonic function, since its growth isn't linear, it's like logarithmic in a sense, what we want to do is we want to, if possible, pick some terminal spanning edge, so that if we have the choice between increasing the W value of a small W value or a large W value, we want to try and increase the large W value, because then that increases very small relative to the smaller W value. And so this is done basically by using the degree, since there's a very kind of intuitive association between W value of a node and its degree. In fact, the W value of a node is lower bounded by the degree of -1. So that's what we're doing here. We want to sort of force as much W value onto as few nodes as possible. And by doing this, we can show that the fraction given this tree has at most a 1.8917 as its upper bound. Now for these leaf adjacent instances I referred to, so yeah, a leaf adjacent instance is when the augmentation problem, every link has a terminal as an endpoint. So then this is the corresponding Node-Steiner tree. And because of the requirement, every Steiner node is thus adjacent to a terminal. So for this case, the witness tree is sort of, we can refer to it as tree following in a sense, which becomes quite clear if you were to contract every edge between a terminal and its adjacent Steiner node, it becomes this tree here. So we've contracted all of those terminal Steiner node edges, and so the actual tree is drawn in black, and the witness tree is drawn in orange. So they're identical. And so we can use some nice little properties about graphs and stuff to find that this has at most H3 or 1.83 as its average. So for these instances, we can get a nice lower approximation. However, as we'll see here, we also have a lower bound. So if we pick our Steiner node tree as this, where all of the Steiner nodes are a path, and every Steiner node has two terminals adjacent to it, then the witness tree is just the path across the terminals, which is pretty clear to see, I think. So then the W value of everything is 3, except for the two endpoints, but we can sort of ignore those for a large value of for a large number of Steiner nodes. And we see that, yeah, basically this sort of means that no matter what witness tree we pick, we couldn't give a better than H3 minus some tiny epsilon approximation for this. So we find that there's a lower bound to the efficacy of this technique. Now, so some open questions and further research that might be of interest. Yeah, so it would be interesting to see if it's possible to apply this sort of approach to node connectivity problems with k greater than 1. And moreover, it would be interesting, I think, to see if you can get a similar reduction for large values of k to k equals 1 or 2 in these sorts of instances. And maybe see about trying to extend this stuff to non-unit node-weighted problems, since this would also give an algorithm for Cactus augmentation, since they both have the same kind of reduction. And one way to potentially just take this analysis and push it further would be just find a better way to pick out witness trees. And so that would be of interest. Lastly, I think it could be interesting to see applying, any of the results from Vera and Rico recently to node connectivity to see what comes of that. However, that said, thank you for listening to my talk.